Okay. Are you able to see the screen? Okay. So let's now we have sort of looked at the state preparation and measurements. Now let's get back to what we mean by density matrix, right? So so the way we define density matrix is we define it as an outer product. So we can say that rho is an outer product of a state psi and psi, right? So for example, if you have, let's say, state 0, right, which we represent as 1, 0, then rho would be, so this 0 would be something like 1, 0. So you could do 1, 0, sorry. You could do 1, 0, 1, 0, right? And then basically that's how you would get the density matrix, right, for that. And so it gives you a 2 by 2 matrix, for example, if you have a qubit system. So the trace of rho will always be 1, right? Trace of rho is always 1 because, like, if you have the probabilities, let's say if you have a state that looks like alpha 0 plus beta 1, then what you end up getting as a trace is alpha squared plus beta squared. So this will always be 1 because the probability is normalized, right? So our worked example is right here that you could see. In general, we could write psi as alpha 0 plus beta 1. And so alpha squared plus beta squared must be 1 because the probabilities are normalized. So if I want to explicitly write this, so then I could write psi as alpha 1, 0 plus beta 0, 1, which is the same thing as alpha and beta, right? And then to calculate rho, the density matrix, I would do psi and the bra, right? So then that would be alpha beta and alpha star beta star, right? We take the complex conjugate there. So then what I would get is alpha star square alpha, right? And then I would get alpha beta star, right? Beta alpha star, beta star beta, right? So this is alpha squared and this is beta squared, right? So that would be the density matrix for this state. So it is equivalent to saying that the state is alpha 0 plus beta 1, but then you see this rho is equal to alpha squared, and it looks like this. So the diagonal elements encode the probability. So when you sum the diagonal elements, you're always going to get 1. So the trace of rho is always going to be 1, no matter what. And these off diagonal elements tell you about basically about interactions, like off diagonal elements. We'll see more what the off diagonal elements mean, but they're telling about how you have this alpha beta star and alpha star beta. So the outer product, it depends upon the chosen basis. So whenever I write this as 1, 0 or 0, 1, this is in some basis that I'm using to write. Like 1, 0, I'm calling it as spin up, and 0, 1 as spin down, or whatever basis I have. It is dependent on the basis, but the trace is independent of the basis. So the advantage of this method is that when you do the trace, the trace is basis independent. So when you want to look at the expectation values, you could just take the trace of, for example, rho m, and that becomes basis independent. Like I said, the diagonal entries always code for probabilities, like you see here, alpha squared and beta squared, right? So we can think of these diagonal entries as weight or likelihood associated with each classical state. Classical state, again, meaning that, remember that we pick this sigma is equal to 0, 1. So this 0 or 1 is what we are calling as classical state, meaning that if I call it 0, that it belongs to, like, this label 0 belongs to this state 0. The classical label 1 belongs to state 1. So that's why it is saying classical state. right? So the off-diagonal elementary entries describe the degree to which these are in superposition. So you get alpha beta star and beta alpha star, and you also get the degree of relative phase, right? Which you can see that, for example, if I have b to be some e to the power I theta and alpha to be some e to the power I theta 2, then you get this to be theta 1 minus theta 2 or whatever that is, right? So so you essentially, like for example, let's say I have some e to the power I theta 1 for the first state and e to the power I theta 2 for the second state. So when I do something like alpha star beta, that gives me something like e to the power minus I theta 1 times e to the power I theta 2, right? Or e to the power I theta 2 minus theta 1. So it gives me the relative phase. The global phase itself, if the wave function has a global phase, that global phase wouldn't appear because it would just cancel out in the complex conjugates, right? So the diagonal entries give you the probabilities, whereas the off-diagonal entries give you the degree to which the classical states are in superposition, and it gives you the relative phase. So that's what we are saying here, same thing. That if you have a global phase e to the power I theta, the density matrix for phi and psi would be exactly the same, right? So so density matrices would then remove this global phase. For example, if you see that here I define phi as e to the power I theta times psi. So if I were to take so if I start with phi is equal to e to the power I theta times psi, and I want to take the rho, which is phi times phi, right? You see that then I have to do e to the power I theta psi, e to the power minus I theta psi, right? So then these go away, and this is same as psi psi. So if you have a global phase, this is a global phase because it's multiplying every single component of psi. So then if you have a global phase, that wouldn't matter because then you get the same thing. So there is no global phase that is encoded in the state. But if you have a relative phase, that would appear in the off-diagonal elements like we just saw, right? So if we have two quantum states and their density matrices are equal, like this phi and psi, then for all practical purposes, we would say that they're operationally identical, meaning that if I measure different observables on those, then I would get exactly the same results. So let's say I have two density matrices rho and sigma, right? I have two density matrices rho and sigma, and I measure energy, right? And if I measure energy, the energy expectation value I'm going to get is trace of E times rho or trace of E times sigma, right? So if rho and sigma, if these traces, if the expectation values are equal, then if rho and sigma are equal, their expectation values are equal. If recall that we saw the property, the linearity of the trace. So for example, if I had trace of alpha A, we could write that as alpha of trace A, right? So if I have trace of E rho, I can write that as E times trace of rho, right? So similarly, I could write trace of E sigma as E times trace of sigma, right? So here, if the rho and sigma are equal, right, even if they differ by a global phase, then it doesn't matter. We get the same expectation value, right? That is, we get trace of rho is equal to sigma, right? But if you have a relative phase, that is, let's say here, global phase, no effect. That is, if I start with psi, that is,
Excuse me, Professor.
yeah,
I just have one question.
yes.
This equality between the trace of
Mhm.
sigma or rho does this imply that off diagonal is also equal in the equality above? Yeah, here.
Here,
Not
yeah, it is.
above.
It's the same thing. So for example, psi and phi, let us say, right? Even the off diagonal elements also will be equal because e to the power I theta, when you have a global phase, it will cancel out, right? So for example, when I take psi, if I take psi as alpha 0 plus beta 1, right? Then that is nothing but alpha and beta, right? So if I want to calculate rho for this, then that would be psi, right? Which would be alpha beta and alpha star beta star, right? So then that would give me alpha star alpha, alpha beta star, right? Beta alpha star beta, right? Now, if I do that for phi, which is e to the power I theta, that is multiplying alpha 0 plus beta 1, right? Then my matrix would be e to the power I theta alpha beta. So when I do sigma for phi and phi, right, I would have e to the power I theta alpha beta and e to the power minus I theta alpha star beta star. So this would still be equal to alpha beta alpha star beta star, which is the same, right? So then rho would be equal to sigma if you differ by a global phase. Does that answer your question?
Yes.
So the off diagonal elements will also be the same if you have a global phase. But if you do not have a global phase, but what you have is a relative phase, like plus and minus states, what is there is a relative phase. That is, the first term is the same, but the second term is negative one here in the negative state, right? So if you take the density matrix for plus versus density matrix for minus, then the relative phase is different, so the density matrix would appear different. Am I making sense there? Did that address your question? I don't know who asked that
Yes.
question.
Yes.
Okay. So if you have a relative phase difference does matter. In fact, we are going to later see that it is this relative phase difference that makes practical quantum computing possible, like especially in Josephson junction, which I alluded to a bit yesterday. So it is the relative phase difference between the wave functions that basically allows us to manipulate qubits, right? So again, this question was asked earlier. So why we need multiple bases, right? So why we need is because off diagonals live in X and Y, right? So if I just consider only one basis, then I may get only the Z components, right? It gives you, like, for example, Z basis. If I set up a Stern-Gerlach experiment along the Z basis, like for example, if I look at if I look at the sigma X, that looks like 0, 1, 1, 0. So you see the off diagonal elements are in X basis or Y basis. If I look at sigma Y, that gives me 0 minus I, 0 off diagonal again, and sigma Z would be diagonal 1 minus 1, 0. So we want to compute with all the different bases because we want to get off diagonal elements as well. So the coherences, the relative phases, are in off diagonals which appear in X and Y if you are measuring along Z axis, and the diagonal elements appear along the Z axis. That's why we want to consider all the bases so that we can reconstruct the density matrix. So in general, any 2 by 2 any 2 by 2 matrix can be expressed as the poly matrix, right? A combination of poly matrices, because the sigma X, sigma Y, sigma Z, along with the identity matrix, span the basis. So any density, any 2 by 2 density matrix, I could express it as a linear combination, right? Any 2 by 2 matrix, I can express as a combination of my poly matrices, right? X, Y, Z. And the coefficients would be basically be the expectation values of those, right? Or the poly expectation value. So that would be trace of rho X, trace of rho Y, trace of rho Z, so on and so forth. So if we want a worked example, let us say we have plus I, where we are taking some state that looks like this. This is a Y eigenstate with eigenvalue of +1. That is spin up along Y axis, right? Then if I want to construct this, then basically think about this. This is spin up along Y axis. That means if I send it through X or Z, then half the time I'm going to get spin up, half the time I'm going to get spin down. Do you agree?
Yes.
Are you with me? Yes. So half the time you're going to get spin up and half the time we are going to get spin down, right? So that means that average expectation value along X would be 0. Average expectation value along Z would also be 0. So then following this linear combination, what we said, that because these poly matrices along with the identity form a basis, then I can just write the density matrix directly, even without doing like the other way how we were calculating, right? So I can just write, I know that along X, the average of sigma X, or which is equal to the notation that you see on the slide, this is 0 because half the time I would see half the particles would have spin up, half the particles would have spin down. So if I write sigma Z, which is the same as Z, that would also be 0. So if I want to express rho, which is something like half times the identity matrix, right? Like what we wrote here, up here, the expectation value of X times sigma X, expectation value of Y times sigma Y, plus expectation value of Z sigma Z, then I can just basically make this 0 because half the time they would be spin up, half the time they would be spin down. And this is simply 1001, right? And then the expectation value for my Y is half, right? So because I am in half state, right? Spin up. So then I could write half 0 minus I 0. And then if I combine those, I would get the density matrix to be this one, right? Um, so so you see that here you have these off diagonal elements, and that would be revealed, only in like Y basis. If you measured it in Z basis, you would simply get 1 minus 1. For example, if I took spin up along the Z direction, then I would just basically get here 2 and 0, something like that, right? The off diagonal elements won't appear. I hope I'm making sense. Any questions? Okay, so then we will go to what we call as convex combination. This is a very critical aspect. So essentially a convex combination means that the weighted average of points or vectors, whatever you are combining in a convex fashion, all the weights that you are combining in a convex fashion, all their weights should be non-negative and they should sum up to 1. So let's say I have two density matrices. Let's say I have rho and sigma, which are two density matrices. Let us say I pick this density matrix rho with a probability P. Then if I pick this sigma with a probability of 1 minus P, then I definitely know that this is going to sum up to probability of 1 because I'm intentionally putting 1 minus P, right? So P times 1 minus P rho. So this we would say is a convex combination, right? So we can make these convex combinations of density matrix. Suppose we have m states, right? For which, suppose I have states 0 to m, right? For which I can make the density matrices rho 0, rho 1 till rho m, right? And I have corresponding probabilities, right? So that would be P0, P1, Pk, right? Then I can make a convex combination of all these density matrices by combining, going from 0 to m minus 1, that is k goes from 0 to m minus 1, pk times rho k, with the condition that k is equal to 0, m minus 1, pk is going to sum up to 1. So this is the convex combination. That is, all the weights are going to sum up to 1. And all these P0 entries, P0 to Pk, are non-negative because they are probabilities. Right, so I can make these convex combinations of density matrices.
And this
Was there a question?
rho naught to up to rho m, what are these?
Those are the density matrices for state. So state 0 to m, right? So rho 0 would be 0, 0.
Okay,
Rho
okay.
1 would be
Pure
1.
states, pure state density matrix.
Whatever state it is, it doesn't matter. If you have a bunch of density matrices, all we are saying is you can combine them in a convex fashion such that the total weights would sum up to 1. Does that make sense? We're not calling these pure states or mixed states or whatever. We're just calling them states. For any state, you can calculate the density matrix. And from the density matrix, we can combine these density matrices. So if it is a mixed state, then basically you can express a mixed state as a combination of pure states. That's what we are trying to get to. Does that make sense?
So rho basically behaves like a mixed state density matrix, isn't it?
I do not want to talk about the mixed state density yet because we will come up with that. It doesn't behave like mixed state density, right? We will see that that has a very specific definition of what we mixed state density is. So all we are saying is whatever m states if I have, I can combine them in a convex way. I can make a convex density possible. So, but we cannot make a statement about general statement about mixed state that this row must be a mixed state or not, right? So I can combine, like for example, I can do 1 over square root 2 0 plus 1, right? And this would still be a pure state. So I can combine their density matrices, like I can combine half times row 0 plus half times row 1, right? And I can still make a pure state. It doesn't have to be a mixed state. Are you following?
Yes, sir.
Yeah, Saptagiri, that's the same answer for you also. Yeah, it is like you're taking m states. So like I wrote here 0, 1, and so I can take half. We can combine different density in a convex fashion and general another. That's what it is saying. Yes. So now if I want mixture of pure states, I could do that. Like I can take a mixture of pure states. So I could do 0, 0, or I could do plus plus or whatever. I could make mixture of different states, right? So I can get these different elements, right? All we are saying here is that you can have a convex combination, right? The reason that I am trying to say here is that this kind of a combination is not possible with state vectors. That is the point that I want to drive home. Because if you want to make combinations like this with state vectors, then you may end up getting results that don't make any sense. So here, if I have, like, let us say m states, I can combine their density matrices linearly. But now let us take their own state vectors. Can we combine the state vectors like that? Right? So why can't we average the state vectors? Because they lead to sort of different results. That averaging doesn't give you a valid quantum state. For example, I can take one state psi with probability half, and same thing that has a phase difference -1 times psi, right? So technically, these two are should give me the same probability distribution, right? So, but if I average them, I would get total zero vector, which is not a valid state, right? But if I add their density matrices, right? If I add their density matrices, that wouldn't happen, right? I can add their density matrices. That would still give me a physical state. But if I average the state vectors directly, then I would get basically a zero vector. So all we are trying to say is that you cannot average state vectors directly, but you can average density matrices. Are you with me? Any questions? So now maybe this slide will address the question that you asked. So if I begin with some basis 0 and 1, right? And I make another basis out of this, like plus and minus basis, which I call Hadamard basis, where I'm combining 0 and 1, right? So then density of a pure state versus the convex combination, right? The convex combination would be basically rho k times pk times rho k. So here this pk is whatever probability I am talking about for one particular state. So I could say half the time I would find particles in 1, 0, half the time I would find it in 0, 1. Right? Those are the convex combinations that we are saying. So all that this means is that sigma k pk is 1. And when you make, as long as sigma k pk is 1, if I do sigma k pk rho k, whatever is the result, this is a valid density matrix. This matrix is a valid density matrix. That is not necessarily the case with state vectors. In case of state vectors, if you average like that, then you may end up getting 0, like we have seen in case of psi and minus psi. So as long as this is a convex combination, meaning sigma k pk is 1, then if you do this kind of a combination, whatever you get is a valid density matrix, is all we are saying. So now here we are trying to make a mixed state, right? Where I'm combining half rho 0 and half rho 1. right? Then you can verify for yourself that we get such a state and we get half the identity matrix, right? This is a completely mixed state of a qubit, right? Interprets as complete uncertainty, meaning that I do not know whether it is in spin up or spin down, right? Uniform random bit upon any computation, right? I get 50%, I get 0, 50%, I get 1, right? If I combine again plus minus, I would get the same half I. You see? So if I combine plus minus minus minus, I would get the same thing. The density matrix is identical in both cases. That means that you cannot really tell whether you are going to get up or down. Again, this up or down means whatever is the basis. So here our basis is 0 and 1. Here our basis is plus and minus. So this matrix itself looks identical, but the bases are different. Are you with me? So anytime you have two orthonormal qubit states, any two orthonormal qubit states will give you a half of identity matrix. Because if I have orthogonal states, orthonormal qubit states, the expectation value or the average along x, y, and z would be 0. So when you express it as a linear combination of different matrices, identity and the Pauli matrices, I get only the identity matrix. And we call this as the completely mixed state because I get 50%, 50% probability, half and half. Are you with me? So mixtures then are represented by the convex combinations, right? Uniform mixtures, if I have any orthonormal qubits, uniform mixtures would give me always I by 2, irrespective of the basis, as long as the qubit basis is orthonormal, right? So the basis choice in the preparation is not distinguishable once the mixture is formed because everything looks like this. This is contrasting with state vectors because when I average state vectors directly, I may not get a physically meaningful state vector. Are you following me? Does that make sense? So if you want to distinguish between if you want to distinguish between purity and mixed states, this is the condition here. So if trace of rho square is 1, then we call that a pure state, not of rho. Trace of rho is always 1, irrespective of whether it is what state it is, trace of rho is always 1, right? But if trace of rho square is 1, okay. If trace of rho square is 1, then we call that a pure state. If trace of rho square is less than 1, then we call that a mixed state. And for a maximally mixed state, it is 1 by half, 1 by d. So in the previous case, when we got identity by 2, that is, it looks like 1, 0, 0, 1 by 2, right? So if you do trace of this is rho, right? If I do rho square, then what I would get is half, 0, half, half. Again, I multiply half, 0, 0, half, right? So you end up getting 1 by 4, right? And then 0, right? 1, 0, 1 by 4, right? And so if I look at trace of rho square, that would be 2 by 4, which is half. The dimensionality is 2 by 2 for the matrix, and the trace of rho square is 1 over dimensionality. So this shows maximally mixed state, half and half, right? But if the trace of rho square is also 1, then that means then what you have is a pure state. Are you able to follow? So rho itself, Priyanshu, rho itself doesn't have any convex condition, right? In the sense, if I pick one state, let us say I pick one state, just 0 state, right? So when I pick 0 state, this is just one state. So I can write rho for this, rho 0 as 0 and 0. There is no convex combination here. I'm just writing one state, right? So if I do that, then that would be 1, 0, 0, 1, right? So then that would give me 0, would that give me, I wrote it wrong.
That will be a scalar.
Right. No, it will not be a scalar, right? Why will it be a scalar? So it would be 1,
Yeah,
right?
yeah.
And then it will be a 1 0,
0, 0. Yeah.
right? 0, right? So the trace of that would be 1, right? It is not a convex combination, but trace of rho is 1, right? But if I take something like psi, which is alpha 0 plus beta 1, right? Then I can write rho as, so this is just alpha beta, right? So then that would be alpha beta, alpha star beta star, right? Which would give me alpha star alpha, or I'm just going to write it as alpha square beta square alpha alpha star beta beta star, right? So you see here that alpha square plus beta square is 1, right? That is always true because the total probability is 1. So the trace of rho is 1. Now you may think that this is a mixed state because you are mixing 0 and 1. But if you look at trace of rho square, verify for yourself that if you do rho square for this, trace of rho square also will come out to be 1 for this state. So for example, we can do that, right? So rho is alpha square, alpha star beta, beta star alpha, beta square, right? So if I do rho square, right, I would get basically alpha square, alpha star beta, let's say, let me just write it. So rho square would be alpha to the power 4, right, plus alpha square, beta square, right? Then just the trace, I just need the trace. So beta to the power 4 and alpha square, beta square. I'm not going to write these elements. So that would be the diagonal element. So if I look at trace of rho square, I would get alpha to the power 4 plus beta to the power 4 plus 2 alpha square, beta square, which is nothing but alpha square plus beta square to the power squared. But this is 1, so this is 1 squared, so it is 1. So even though psi looks like alpha 0 plus beta 1, you may think this is a mixed state because you're mixing 0 and 1, but it is not, because when I do trace of rho square, you clearly see that that comes out to be 1, right? The total probability is always 1. There is no convexity in that. Convexity condition means that when you combine different things, the weights of those combinations are all non-negative and the sum of those weights is 1. That is convexity condition. When you have only one thing, right, then that doesn't mean that convexity condition, right? So I think Gagi put something, mixed state can't be expressed as kets, only in terms of density matrices. That's right. So I hope you're able to see that this psi, although you write it as, I think there was a question before also about mixed and superposition states. So usually in linear algebra, you would say that maybe like, or in some sense, you would say that you are adding these two linearly, 0 and 1, alpha and beta, right? But that is not a mixed state. You're not, because even the trace of rho square, as I showed you, will come out to be 1, right? Only when trace of rho doesn't come out to be 1, you can write it as this thing. So for a mixed state, I can only write the expression for density matrix in the sense that, for example, we have seen previously one maximally mixed state that is between plus minus and minus plus. Like if we go like this one, right? So for example, if I write this, so the density itself is like half 0, 0 plus half 1 and 1. So this you cannot express this as some psi times psi, right? You cannot express that in terms of like how you express this kets. You can only directly write that as how you are expressing here. So that would have maximum. If you do the rho square, it would give you half. So the trace of rho square is the real check to see whether it's a mixed state or it is a pure state. So we can only distinguish between pure state and mixed states. Pure states are where trace of row square is 1. Mixed states are where trace of row square is not 1. And if it is 1 over the dimensionality of the matrix, then basically it's a maximally mixed state. That is, you will get 50%, 50% chance. Does it answer your question? Is that clear to everyone? Any questions?
Yes, Professor. It's true.
Are you with me?
Yes, yes.
Okay. So any mixture over orthonormal basis basically gives you the same maximally mixed state. So next we are going to do something that's useful later on. It's called the spectral theorem, which we are not going to prove, but essentially the spectral theorem can be done for both normal matrices. Normal matrices meaning Hermitian and unitary, right? So Hermitian matrix, right? In Hermitian matrix, M dagger is equal to M. M dagger is, so if I have a matrix M, M dagger is the Hermitian, meaning that these two are equal, complex conjugate transpose. But if you have M dagger M is equal to identity, that's a unitary matrix. So both Hermitian and unitary matrix combined is what we are calling as normal matrices. Recall that, like, if you have a Hermitian matrix, we saw that it should have non negative real eigenvalues, right? And so here, what we are saying is that if you have a matrix M normal matrix, then you have some orthonormal basis that you can express it in. This basically says that you can find out the eigenvectors and eigenvalues. This lambda 0 to lambda n minus 1 are the eigenvalues of this matrix and the corresponding eigenvectors, and you can express it as a combination of those eigenvalues or eigenvectors. It is called spectral decomposition because that contains the these eigenvalues are considered to be the spectrum of the matrix M, and these kets are corresponding to each eigenvalue, each eigenket. So as long as it is normal matrix, then we can, that is, it is either Hermitian or unitary, then we can express it as a combination of some basis, some orthonormal basis, right? So like I said, each row k is an eigenvalue, right? So if I apply this to the density matrices, then you see that this must be a convex combination, which means that this row k should be a probability vector. These eigenvalues should be probability vectors, right? That is, they should sum up to 1, right? The total trace should sum up to 1. So essentially what we are trying to do is that using rho, we are encoding the same operational characteristics, but it is easier to handle rho than states because these can be added in different ways in which you cannot add kets. Like, we have only considered systems like, for example, alpha 0 plus beta 1, right? We can only consider systems like this. But what if, like, if I have a system that is described by a mixture state like this, right? That I cannot write it in form of a ket like this. I cannot really express them as kets like this, right? So that's why we want to use these kind of systems. Okay, let us go back to composite systems, and I want to do some coding here. So we sort of jumped over what tensor product means, and I want to go back and talk a little more about this tensor product before we move into entanglement and Bell states. So when we say we have two subsystems in a Hilbert space, these are sort of independent of each other. Then we express them as a tensor product, which is shown as this symbol. That is, H1 is independent of H2. For example, I could say I have some electron, right, where the spatial part where I would find it, right, that I can encode in, let's say, psi of RT, right, spatial wave function. But that also has this spin, let us say, right? So then spin can be up or down, right? So then I can combine these spin states, right? This would be the total state. each of these is a subset of the total Hilbert space, right? They're independent of each other. Spin is sort of independent, we're saying, of the position or the spatial dependence, right? But these are kind of independent, and we can combine that to get the total subspace. So the total, when we write a vector, ket vector like this, what we mean is it's a tensor product. That is, we are joining this, right? A density matrix represents the joint state of the composite system, right? So if you have expectation values you want to take, then you simply multiply it with rho, right? And take the trace of that. If I have an operator R, I multiply rho with R and take the trace of rho. So it doesn't matter how many states I have. So I can now maybe do 2 qubits, right? If I have previously, we have looked at only 1 qubit. Like right now, I can look at 2 qubits. That is, 1 qubit is different from, physically different from another qubit. So 1 qubit may be made by 1 Josephson junction, another qubit may be made by another Josephson junction. So we can take these 2 qubits, like I can write states like 0, 0, 0, 1, or 1, 0, 1, 1, stuff like that, right? What this means is I have 2 qubits that are doing the tensor product, right? Qubit 0 and qubit 1. So if I want the total expectation value, I can still use the same thing. That is, I can sum over the diagonal elements, take the trace, and I would still get the same result. And then, you can sort of expand this in the product basis and check. But if I want to get only observables for 1 qubit, so I have a 2 qubit system like this, 0, 0 or 0, 1, but I want to make measurements only on the first qubit. I don't want to disturb the second qubit. I want to make only the first qubit. Then what I need to do is I need to sum over just only the first qubit, and I just ignore the second qubit. I want to ignore the second qubit and only get the first qubit. So to do that, we define this rho 1, that is the reduced density operator for just system 1. First qubit is you sum over the second parts. You ignore the second parts. You leave the second part alone. So if I want to get, let us say, measurements only on the first qubit, I simply ignore this part. So in a combined state, the reduced density operator would be here. This superscript trace 2 indicates that we are summing over the second one, right? For example, if you have a probability distribution of 2 random variables, x and y, with a joint probability distribution x, y, then if I want to find only probability of x, then I sum over all the y's, right? Probability of x would be sum over y of pxy. That is, we ignore the values of y by averaging over. Same thing we are doing. So if I want to do rho of 1, then I take trace, I sum over 2, right? That is, I ignore 2 in rho. Are you with me? Any questions? Any questions? Okay, so let us go to quickly to the code that we have here, and then let's do this multi-qubit. Are you able to see the code? Okay. So whatever we are doing with Qiskit, I want to mention that although we are running it on simulated computer right now, you can use the same code to run on the actual IBM quantum computer, right? So please use these codes for that matter, right? So here I want to show you how basically these subsystems would look like when we make these tensor products. So here we are going to pick 2 systems, right? So I'm going to create state vector. So this is a way to, state vector is a standard thing that you could import in Qiskit. So for example, in Qiskit, you can import state vector, and then all these states like 0, plus, minus, 0, 1, all these are standard. So you could just say 0 is state vector from label 0, right? Or if you want to create a superposition state, you can say state vector from label plus. That would create superposition, right? So here we are creating 0 state from label 0, and here we are creating state 1. So this is qubit 1, this is qubit 2. We are creating 2 qubits. And then if I want to do the tensor product, I can create this 0 times tensor product with 1, right? That is the same thing as I'm writing 0, 1. Okay, you can't see the notepad. So I'm writing 0, 1. This is qubit 0 that I'm initiating in 0. This is qubit 1 that I'm initiating in 1. So then I'm writing my psi as 0 tensor product 1. So I created the state 0, I created the state 1, and 0 times 10 tensor 1. So then I get, this state 0, 1. Right? So similarly, then you can create, for example, plus or minus, and then you can also do like superscript. This is another way to do the tensor product. So this is also tensor product. Or you could do dot tensor, either way. If you do plus to the power minus, it gives you the tensor product. Both will give you the same thing, right? So now this would be the tensor product between plus and minus state, right? So you can also display the plus and minus states if you want. Now let's see. Let's say I want to ask you a question to make sure you're able to follow me. Let us say I take two operators. Let us say I take the Hadamard operator, which is 1 over square root 2, 1, 1, 1 minus 1. Let's just call this H1. This is Hadamard operator for qubit 1, right? Let me take another one. Let me take a poly NOT gate for something else, 0, 1, 1, 0 for qubit 2. Right? So this belongs to qubit 2. So this is a qubit, meaning it has 2 states. So this is a 2 by 2 matrix. This is also a qubit. So this is also a 2 by 2 matrix. So when I do H1 times X2, what is that going to be? Is that going to be a 2 by 2 matrix? Please answer in the chat.
4 cross 4.
Okay. So we have the answer is 4 cross 4. Let's see. Anyone else?
4 by 4. It's a tensor.
Okay. I heard 2 answers. Everyone else? Are you following me? Okay. Okay, so let's see. So I'm creating this Hadamard operator, and then identity is just identity matrix. And this poly X is the X0 gate. Then let's see how to take the tensor product of these matrices, right? So what I'm doing is I'm taking the tensor product of Hadamard and the identity matrix, right? Hadamard and the identity matrix. That is, I'm taking this and the diagonal matrix, right? So then you see you got a 4 by 4 matrix, right? That is, so essentially I am picking this and putting it in each and every place. Like for each element I get a 2 by 2 matrix now, right? There are 4 elements, but for each element now I get a 2 by 2 matrix. Are you with me? Okay. So similarly, you can do 3 matrices, right? So 2 by 2, 2 by 2, 2 by 2, right? So then what are we going to get? You repeat this and you can see how you can build that, right? Okay. So the next question is, suppose we build some operator X tensor product with Y. That is, X is applying poly X gate, that is Stern-Gerlach along X axis. Y is applying Stern-Gerlach along Y. So if I build an operator like this and I apply it on a state that looks like plus tensor product with minus, does this equal to applying X on qubit 0, which is plus state, and Y on minus state? What do you think?
Yes.
So I have X times Y, and I am applying this on plus times minus, right? So what I'm saying is this equivalent to saying x plus times y minus? Is that right? Yes or no? Okay. Okay, Shafna says no. Anyone else? Are you guys able to follow me? Is it that you're not understanding the question, or I would like to see more answers? I just see only, okay, I see some say yes, some say no. Okay. Okay. So some say no, some say yes. So let's check it out, right? So now there is another thing that we can download from Qiskit. That is, we can import operator in addition to state vector, right? We saw state vector that can create states like 0, 1 and stuff. But we can also import operator, right? Using which we can define the matrix, right? So of course, you can do this in NumPy also, but then you cannot use NumPy on quantum computers. So that's why we are using Qiskit here. So just like how we created the state vectors from labels, you have all these labels like X, Y, Hadamard gate, H. You have all those available in Qiskit. So I'm creating X operator. So this X operator looks like this, 0, 1, 1, 0. And then Y operator looks like 0 minus I 0, right? And so when I do XY, if I want XY, that is, I want Y to act on the second bit and X to act on the first bit, right? Then I need to do Y dot tensor X, not X dot tensor Y. Okay. So when I do, we will see the difference. Note that here I am doing Y dot tensor X. Then I'm creating plus state. Then I'm creating minus state. I'm taking phi as the tensor product, right? And then I'm going to apply this phi on the combination, right? So then if I display phi and this thing, right? So then you get this answer, right? So if you have x dot tensor y versus y dot tensor x, you will get different answers. So this is what we got for y dot tensor x. So if I did x and dot tensor y, you note that we will get slightly different answer, right? So now let us check if the question that I asked is correct or not, right? So for that, what I'm doing is we are applying the tensor and I'm going to evolve with phi is equal to xy, where I'm defining xy as this one, y dot x. So this, if you want x times y, when we write like this, that you need to define as y dot tensor x, not x dot tensor y. That's what I was trying to say in the previous one. We are in the superposition of yes and no. Okay. Okay. And then we are going to create a quantum circuit with two. That is, we are going to create 2 qubits, right? And I'm not putting any classical bits here because I'm not trying to store any information. I'm just going to output that, right? So, so the Y is going to act on the right one. X is going to act on the left one, right? They are acting on the 2 qubits. So what I'm doing is I'm evaluating this, right? So I'm evaluating X on one bit, Y on the other bit, versus I'm going to do this one where I have phi of xy. That is, I'm going to directly operate x times y on this superposition state plus times minus, versus comparison of doing y on the 0th qubit and x on the second qubit, right? And so let's see what we get, right? Matches x times y, it is false. If x is on q0 and y is on q1, are they equal? True, right? So basically, if I change this to now x dot y, then you will see that they would match. So now you see that matches xy. Yes, it is true. But does it act on Q0 and Q1? No. That means that when I write in the code, when I write y dot tensor x, this means y acts on qubit, the second qubit. So this means y acts on the second qubit and x acts on the first qubit. So whatever you want to act on the first qubit, you put that inside here. So if you did x dot tensor y, this would be equal to y, something like this, y times x. This would be equal to x times y. Are you able to follow me? That's what I was trying to show there. And then you can also create an n-qubit superposition. For example, you don't have to be limited to 2 qubits. You can create 3 qubits, right? That are like qubit 1, qubit 2, qubit 3 that are in a tensor product. So you can just take state vector from label plus, right? That is each qubit is in this, and I have 3 such qubits, right? Then you can just basically do things like, just keep multiplying them with the tensor power. And then because you have 3 qubits, each qubit has 2 states. So you get 2 cube, you get 8-dimensional state. So that would be the total state that is generated. Are you able to follow me? So you can generate other sort of 3 qubit states too. We'll talk about this GHZ and W states later on. So we will see how that is different. So basically the idea of showing you right now whatever I did was to show that you can how to make these tensor products, and then you can do the measurements. That is, I can measure only on. So like I made this state vector, let's say this one, W, the state vector looks like this. There are 3 qubits. You see here 0, 0, 1, 0, 1, 0, 1, 0, 0, right? And then I am going to measure only on 0th state. Like in the sense that I'm going to make only measurements on the 0th qubit. Or I could measure 0th qubit and the first qubit. Or I can measure all 3 qubits, right? I can pick and choose what to measure. And after I measure, the state will be different based on what I measured, right? So for example, if I measured the 0th qubit to be in this, right, then the state is going to be changed to state of measurement is going to be like this, right? So I can run it again and then the state might change, right? So if I measured 1, then I would get, this state. So I can measure different qubits. I'm doing single shot measurements here, right? So I can measure only 1 qubit, right? Are you with me? Are you able to follow what I'm saying?
Can you repeat this part?
Okay, sure. So here we are expressing a we are expressing a 3 qubit state. So here the first qubit, if you look at it, it is in 0. Here also it is in 0. Here it is in 1, right? Second qubit, here it is 0. Here it is 1. Here it is 0, right? So on and so forth. You're able to see that. Do you understand that?
Yes.
Okay. So now if I make a measurement on the first qubit only, right? If I make a measurement on the first qubit only, then I should get either 0 or 1, right? Either 0 or 1, right?
Yes. Okay, I get it.
So if I make measurements on like, so if I make measured on the 0, so this is indicating the qubit state, right? The number of qubit, whatever qubit I'm measuring, then I get this state, right? I'm measuring the first qubit state. On average, I'm getting this. So you can change the state vector to be whatever it is, and then see out of 3 qubits, I can just measure 1 qubit. That's what I'm trying to say. Does it make sense now?
Yes.
Or okay. Then let's get back to this one. I think I have to run everything now. So I want to show you this one of how we are getting the density matrix. We saw the subsequent measurements. So now I want to obtain the density matrix by measuring things, right? So we are here simulating this, right? So what we are going to do is we are just trying to start with prepare a state which is in 0 and 1, right? Plus I state, and we're going to do 4,000 shots. So like I said, you can make the density matrix. You can make the density matrix rho as I by 2, right? Plus half x times x plus y times y plus z times z, right? So that's what I'm doing. So I prepared the qubit in plus state. I am measuring it in. So when I'm saying I'm preparing it here in the code, I know because I'm still writing it as a classical code, right? So in real experiments, we don't know this, right? We're going to just initialize. And then if I want to write the density matrix, that is if I have a state preparation procedure, but I do not know the density matrix for that state preparation procedure, right? Imagine that you did not know this part, right? Some state is prepared and I want to determine the density matrix for that. Then what I do is first I measure along Z, find out expectation value of Z. So then I get this Z. Then do the same thing for Y, same thing for X, right? So that's what we are doing here, right? So I prepared the state. I'm measuring the EZ. So I'm doing 4,000 shots. I'm doing 4,000 shots so I can get an expectation value. I can get an average value. And so from there, I'm getting expectation value of count Z, and then expectation value along X, expectation value of Y, and then I'm doing the linear combination of whatever is the X, Y, Z matrices. And then you can see the combinations, right? And from there, you can build the density matrix. So my density matrix would come out to be, the reconstructed row would come out to be this. That is 0.5 minus 0.5 J. So this looks like half minus half J for half I, right? Half I and half. So that's the density matrix for whatever state I prepared. Were you able to follow me? How to construct that full density matrix? This would describe the total. For spin, we're doing X, Y, and Z. So I can encode the probabilities for all X, Y, and Z. So this would describe the total state. Are you with me?
Yes, Ram. So this process is fixed for all, right? So I mean,
Yes.
this is,
yeah.
if you want to construct a density matching, this is the order we should follow. X, Y, Z.
Yeah, X, Y, Z. Right.
Okay.
I mean, for any 2 by 2 matrix, that we can express it as a linear combination, right? So here, the only thing that I want you to understand is here I'm sort of faking it in the sense that I already know what the state is. Like I could have calculated it from here itself, right? But that is when you're doing math. But let us say you have some state preparation procedure, experimentally speaking, you made a state preparation, experimentally you made some Josephson junction or heated silver atoms or whatever, right? So you do not know like what the state is yet. You want to actually establish the state from the preparation procedure. Then what we are doing is we are measuring the expectation value of Z first. Then again, we are not measuring expectation value of X and Y after measuring the Z. It is repeat of prepare and measure. So you prepare, measure Z, then prepare and measure X, prepare and measure Y, and get expectation of X, expectation of Y, and expectation of Z, and then combine them to get the total row. Does that make sense? Is there a question? Okay. Are there any questions on what we are doing?
So I see we are measuring that the first bit, right? I think this is just for the example.
This is only one qubit.
Okay.
This I created only one qubit state.
Okay.
But you could do that on, so if you have multi-qubit state, right? then what you could do is you will have to do, like for example, you can create a tensor product of qubit 1 and qubit 2, and then you do these measurements on qubit 1 and qubit 2, both. Are you with me?
Yes.
So here we're doing only for one qubit. You can repeat this exact thing on the second qubit. That would be independent. And then you add those two matrices.
So for each qubit, we have to run a loop.
Right. For each
EZ.
qubit, you have to run a loop. Right. That's right.
And this there is also an probability in the x basis in the row ex. There is a small probability in the ex, right?
You mean in the result here?
Yeah. But you didn't.
I mean, that is
mention
because it is the way it is. It is if I run more shots, let's say if I run 40,000 shots, it will go to 0. It is just because the way the computer works, right? So I hope it went to 0. Right, it decreased. Now it's like 0.0006. Right, so it's just an artifact. So you can, so you see this is e to the power -4. So it's almost equal to 0. So I would just ignore that. Right, so yeah, so this is 0.5. This is 0.5. This is,
and
this
it's a
part is
negative.
Negative 0.5, that's right. But this part is 0. Right, so it looks like this, right? Half minus half I, and half. Right? So the exact one would be this. So this exact one, because we defined the state, we can compute it like by doing plus I. So if I'm doing it on paper, I can do it like this. But experimentally, when we make qubits, I do not know the state. You see, the thing that I'm trying to get at is, maybe I need to, I don't know how to frame it. We get so engrossed in the math that we know that the density matrix, how to calculate it, compute it on paper, given a state. But experimentally, when I make some system, I do not know what the density matrix is. It is not like the thing that comes out of Stern-Gerlach is going to give me plus or minus or whatever state. I do not exactly know. So if I want to determine the density matrix of a state preparation procedure, it is preparing a state, but I do not know what that state is. Then this is what I do. I make multiple measurements along X, make multiple measurement along Y, make multiple measurement along Z, get their expectation values, combine them, and get the row. Once I get this row, then this total row is what is telling me my state. So going back to the first question that we had earlier in the last lecture, when you make a single measurement, you cannot get this. When you make a single measurement, you don't get the state. Are you able to follow that? There is no state in the single measurement. It's a single outcome. So when we want to construct density matrix, we have to make multiple measurements. That's the point that I want to make in terms of this. In fact, I think I have as a homework to make for multiple qubits, to do this for multiple qubits. So I think you should receive the code through Dr. Gargi will email the PowerPoint, and so you should be able to get those. We are running out of time, but very quickly, I want to talk about entanglement. So okay. There are too many slides. We can talk about entanglement maybe tomorrow, first lecture, but essentially what entanglement means is that, let us say here, let me use this picture and talk about this. So let's say there is some source here in the center and I build some box around it. This is my state preparation procedure, how I am building an entangled state. I make some holes on both sides. Every time this emits something, this source, it emits two particles such that they have equal and opposite momentum. That is to say that here you have Ka emitted this way and Kb emitted this way from the particle. Are you able to see Ka and Kb? So we say that Ka is exactly equal and opposite to Kb minus Kb, right? Similarly, Ka prime and Kb prime. So the particle, the source can emit particles in any direction, but we are cutting holes only on both sides. So any other particle, for example, if it is emitting particles straight up, those would be blocked because we did not cut a hole there, right? We are intentionally cutting holes on the opposite sides, right? And so whenever it emits particles, it emits in opposite directions with equal and opposite momentum. Now you see I put mirrors here on both sides. So when I combine, right, when I get this, right, whatever I am getting here or whatever I am getting here, right, it is that when I measure the whatever is the state of here, the what if I measure this momentum to be, let us say, kb, right? Then the momentum that I measure here, there is a correlation with, if it is kb here, then it will be ka here, because that's how they were emitted, right? But I cannot really tell which one is which. But if I measure kb, whatever measurement I make here is sort of correlated to the measurement here. So those kind of correlations is what we call as entanglement, right? So, and we write the state like this. So we will talk more about these entangled states, which have to do with correlations or interference patterns that would arise. We'll see how those arise. And then discuss these joint probability distributions. I think probably this will be done in the first lecture tomorrow. And then hopefully we'll get to transmon preparation. So I will stop here and wait to see if you have any questions. Thank you. If you do not have any questions, you are welcome to leave.
Thank you.